In this video, we are going to look at regular expressions. So regular expressions are another presentation of regular languages. Okay, so we know that regular languages are languages accepted by DFAs. And we know that DFAs are equivalent to NFAs. Okay, so today we're going to look at regular expressions, which are a different way to represent a regular language. Okay, so sometimes, actually, in many cases, a regular expression provides a concise description of a regular language. Okay, so provides. Okay. So, for example, in a previous example for a language L, that consists of all binary strings with one on the third position from the right. We can represent this L by the following expression. So we know that, so here from the right, the third position is a 1. And from the right, the second position could either be 0 or 1. So this is 0 plus 1 means either 0 or 1. And then, of course, the symbol at the end is also either 0 or 1. And before this one, it could be any binary strings. Okay, so that is 0 plus 1 star. So this is the sigma star. Sigma is 0 and 1, which is a binary alphabet. Similarly, we can represent all binary strings with 0 on the second position from the left by this regular expression. So this is the second position, this is 0. So the first position could be 0 or 1. And anything after, any strings after this second 0 could be anything. So that's 0 plus 1 star. So in these examples, we use all three regular operations. We use a union, which is plus. Of course, we can also use this notation. And we use concatenation. So this is the first position, second. So this is here is a concatenation. And of course, we use a star. So the same language may be described by multiple regular expressions. For instance, 1, 1 star is equal to 1 star 1. Okay, so in other words, regular expressions may not be unique, but they represent the same language. Okay, now let's define regular expressions formally. So we say that R is a regular expression if R is either is, okay, so one of these situations. So A, which is a symbol, alphabet symbol, representing a set of A, singleton set of A, or empty string, okay, representing a set of empty string, or just empty set, or R1 union R2. Sometimes we also write it as R1 plus R2. if R1 and R2 are regular. So in other words, you can see here, this definition is a recursive definition. We first define the simple case, and then we build on these simple cases. So of course, we first know that a symbol is regular, is a regular expression, and then an empty string is a regular expression, and an empty set also is a regular expression, and then we can use union based on these. Okay, we get a new regular expression. We can also use concatenation and star. So we can then come up with a regular expression using these three operations, regular operations, based on these basic regular expressions. Okay, so sometimes we may also add parentheses to avoid confusion, for instance. Hence, we have this. So if you have a set 0, 1 star, it is, we can write it as 0 plus 1 star because this set is 0, 1. It doesn't. So this is 0, union 1. So singleton set 0, union singleton set 1. So we know that we can represent it. So the 0, union 1, or it's more convenient to write it as 0 plus 1. Hence, if you put a star here, it is just, now we use parentheses. Okay, so to indicate this star is for this union, and then this, and then that. Okay, so so this is one way to write a regular expression. So I prefer 0 plus 1 parentheses star. And then 0 star followed by empty string is just 0 star because 0 star concatenate empty string. It is a set of 0 concatenate an empty string. So this is will be because so the multiple zeros are followed by an empty string. It just the same multiple zeros, and this star includes empty string. So this is the same. Okay, so which is a 0 star. And if it's followed by an empty set, okay, then it is just empty. All right. Because you concatenate an empty set, it's just nothing. And we also use a 1 plus to indicate that it is a regular expression that consists of at least 1. So then it is equal to 1 star. And then 0, 1 plus star is a set of all strings x such that every 0 in x is followed by at least 1 ones. Okay, now remember this is a star, so that means it's a string over this alphabet. Okay, so that means it's a 0 and followed by at least one, but could be a lot of ones, right? But at least one, and then so each string will be just like, so each symbol will just be like that. So in other words, you can think of this 0, 1 plus. Okay, so this is just a set of 0, 1, 0, 1, 1, 0, 1, 1, 1, right? So this represents this set. And then you put a star. Then this means that these are your basic strings, and it will be a finite string x. Okay, x will just be formed by using these elements. So that means a 0 followed by multiple ones, but at least one. Okay, so it's followed by at least one, right? Okay, so it could be, for instance, could be, for instance, x just 0, 1, 0, 1. Just use this repeated, use 0, 1 repeated many times. And then you could also have 0, 1, 1, or 0, 1, 0, 1, 1, 1, right? So that really means that every 0 in x is followed by at least 1, 1. Okay, now let's look at a result. This is a theorem. L is regular if L can be described by a regular expression. So we prove it by induction. So first, it is straightforward to see that a set of empty string, and empty set are regular. So we can see that here we can, for A, we can use the following automaton to accept it. So this initial, this is the final, and this is A. Okay, so, and then for empty set of empty string, okay, so it just means that it doesn't take any input. So that means initial is also final. And for empty set, just means there is no accepting state. It does not accept anything. Okay, so these so these are regular. Okay, so and then of course we can represent this as singletons. So this is a just empty string, and it's just an empty set. And then we can and then the regular expression would be like the hypothesis will be assuming when the length of, so this is induction by the length. So when the length of less than or equal to k, then R is regular, and then for length k plus 1, we know that it could either be, we could write down as, so this R will either be R1 union R2, or R1 concatenate R2, or R1 star. So if R is k plus 1, then these R1 and R2, the length of them will be less than or equal to k. So by assumption, they are regular, and and then a language that can be described by R is a union of a language described by R1 and a language described by R2, and we know that's regular by hypothesis. So this is irregular by hypothesis. So union of them, we know that it's regular. So that's L of R. Right. So this is straightforward using induction proof. Okay, so now let's look at an example. How do we come up with a NFA for a regular expression? Okay, so we have here's AB plus A. So we first write down A, so which is this NFA, and B is this, and then AB, you just connect these two by using using an edge with a empty string as input. So that's concatenation, as we see earlier when we look at closure properties for regular languages. Okay, so then AB union A, so this is A, so union, we just add a new state, initial state, and add a empty string edge from this new initial state to the initial state of AB, and likewise to A. So we put a cleaning star, so we just make a empty string arc back to the initial. Okay, so this is back. So that's the construction. And the other way around is also true. So if L is regular, then it can be described by a regular expression. So then the idea is the following. We're going to generalize NFA to allow a regular expression as an edge label. Okay, so not just a symbol or an empty string. So in other words, what we had before for a NFA, what you get is for each edge, you will either be a symbol A or an empty string as input. Now we generalize this to allow a regular expression. So there's R. So R is a regular expression. Okay, so it's a regular expression. For instance, here I have 4 states. From Q star to this state, it is A, B star. So this is a regular So AB star is a regular expression. So any of these except that, except this are regular expressions. So then the proof of this theorem is to reduce states until we only have, so basically we're gonna add a new start state, a new accept state, okay, to a given NFA, okay, and then we're going to remove all of these nodes except the ones we added, and whatever left is a regular expression. That's the regular expression representing this NFA. Okay, so this is the NFA given, this example, and we add a new initial state S, a new accept state A, and remove the accept state from the original machine, but we make a link from those accept states, make an empty string link to this new accept state. Okay, so if you have more than two, for instance, if you have more than two final state, accept state, okay. That is so what you're gonna get is I introduce a new one, that's a QA or A here, and then we make an arc empty. So cannot write it. Oops. And then this remove. Okay, so that's what it is. And then if this is initial, then we just add a new initial state. All right. So in this particular case, we add S, we add A, and then we're going to remove 2. So removing 2, we're going to look at this path from 1 to A. So on this path, you first have B. And then here, A or B, you keep looping on 2. So since you remove 2, so you have to make this the regular expression on this path to be the new label on the edge. Okay, so this will be just from 1 to A. Okay, so that's here. Now we remove 1. So from removing 1 is an epsilon A star followed by B followed by A union B star. So that's what we get here. Okay, and let's look at the other way. So you're given one more example is DFA. We want to get a regular expression out of it. So this is a given DFA. So we add a new initial state S with an empty string length to 1. We have 2 accept states here. So we add a new accept state A, remove the double circle from 2 and 3, and make a epsilon or empty string link from 2 to the new accept state, from 3 to the accept state. Okay, so that's what we have. And then we're going to remove these nodes. In between this S and A, remove them one at a time. So let's say we remove one. So by removing one, then I have to, that means I have an edge S, okay, so this is going to 2, and here is going to 3, all right? So that means now let's say removing 1, I will have from S to 2. So this would be A, right? So this will be A. And then from S going to so removing 1, so I have here and going to 3, so that means S to 3 is B. So S to 2 is A, S to 3 is B. Now, and also I have this loop. As you can see here, I have, because this one is going to be removed. And so you can loop this A, and then see from here you go to A, and then so 1 is removed. So from S to 2 is A on A going to 2. And then there is a loop here, so that is AA. So that means it's AA or B, right? So we just keep looping. So either going this way or going this way, and then you keep loop. So that's AA. So that's what you have over here. All right, and then so 1 is removed. So there is a pass, okay, that goes through once from 2 to 3. So that means now from 2 to 3, I have a direct link with this regular expression AB. So that's what we have. And then also from, see, so 1 is removed, but from 3 going to, so 3 going this way, and that, so that's BB. So that means you have a loop. And also from 3 through 1 going to 2. So 3 to 2 has an edge, which is BA. So that's what we, which is BA. Okay, so that's 1. And the original is A. So that's BA or A. Okay, so that's what we have by removing 1. You consider all paths that goes in through 1. And then each of those paths, after removing 1, you use a regular expression to represent that 1, to represent the effect that 1 is being removed. So that's what we get here. And then next, we're going to remove 2. Okay, so we're going to look at the paths, all the paths that go in through 2. So 1 is from S to A. So that now I have a direct link, S to A. Now we are going to check this path. Okay, the regular expression for that path is A, and then AA union B multiple times. That is Kleene star, right? So that's what we have. And then let's see, moving to the path, we are going to see here is 3, okay, going to 2. So 2 is being removed, and this, now I have BA or A, and then followed by AB, okay, and and now this is two original here, right? So you go BA or A, going through this many times as you want. So it's AA union B star and then AB. Okay, and the original one is BB. So that means that after 2 is removed for this 3, you have BA union A, followed by AA union B star, followed by AB. So that's what we have here. And BB is original, that means OR. Okay, so that's, so that's from 3. And then, so we have, okay, you see this. This is 3. You can go to 2 many times. And then, sorry. So going to 2 and then going there. So that means from 3, I have a direct link to A. But since 2 is removed, I have to add this regular expression. So there's a BA or A followed by this guy AA or B star, and followed by epsilon, then that's itself. So that's what it is. But I have is epsilon here, so that means or epsilon. Okay, so that is removing 2. So now we are removing 3. So removing 3, I have this pass. Okay, so that's S going to A, but we have to add this pass. So that means this is the original A, AA union B star. So that's OR of this. And then this part is this guy followed by this guy. So this guy would be star and then followed by this guy. So that's what we have over here. Okay, so this is here. And then this part is star and followed by this. That's what we're getting. And then or this thing. So finally, we get a regular expression for this automaton. So that, so from here, we know that we can use a regular expression to represent a regular language. Similarly, for any regular language, we can find a regular expression for that language, for that regular language. Okay, so that is the end of this video.